stat pack and you went running.
That's just the first step. The next step is through the window.
Oh. Do you
Okay,
have
but
enough?
I know all about that.
Zane, do you have enough energy to tunnel through it?
Yes. Just barely.
Seems a little unnecessary while it's open.
Sure.
Still takes energy to get up and go over there.
Enough energy to barrel through it, not enough energy to open it.
You can make that joke.
Two different types of brain brain usages.
This is a summary we discussed so far. I introduced the general angular momentum, and we discussed its commutator relation or commutation relation. We introduced J plus minus so we can determine the eigenvalue, allowed eigenvalue of J square and Jz because they mutually commute. Since the commutator relation between the components of angular momentum does not commute each other, so we only can select two pairs, either J square with Jz or J square with Jx or J square with Jy. So we select this pair. Then we use the J plus minus to obtain this allowed eigenvalue for J square, which is controlled by the quantum number J. And this quantum number m is characterized the eigenvalue of J3. So you can see here we already obtained that J allowed value is from 0, 1, 0, half, 1, and 3 half, 2, 4. So either the integer number over half are the integer number. Then for giving J value, we will have 2J plus 1 allowed M value. Actually, later we're going to use this Mj, but here use M is fine. So this is for two quantum numbers. Now, today we continue discuss the general angular momentum. Then we go to the spin. The geometric representation of this angular momentum, we can also use graphic to plot this relation between J square and Jz. So let's consider this magnitude of this J square. Now I'm going to use index here. This means this expectation value for J square in this eigenstates, right? Not arbitrary states. So this gave us, because we know this eigenstate of J square, so we have the eigenvalue here, that is H bar J plus 1. So that is the magnitude of J square, sorry. Then the Jz, again, is in this eigenstates of this joint eigenstates. So that should be Jm, Jz, Jm, and that gave us here H bar omega, right? So, okay, not square, right? that is good, that is good. So that's H bar M. Sorry, H bar M. So now, if we plot it, if this is a vertical, we use as a Z, GZ, and then this horizontal X1, I put together a side view. Then we can see if we have this magnitude of J squared is here. Okay, so that magnitude is H bar J plus 1, right? And then this give us the direction and the magnitude so that for all the same, any direction will give us the same of magnitude, but this orientation different, right? So they project to the Z axis. This gives us Hn, right? That is for this alpha m here. Then since we know the m is quantized, it does not mean this angle can arbitrarily in the space continuously. It only allows sum of values. Here, here, and here, right? So that means according to this case, they project to this z direction only have some of loud numbers for given magnitude of J. This is graphically to express the angular momentum here, and the alpha depend on m, right? Depend on the angle that project or angle of this total angular momentum with respect to either Jz or Jxy. So you can see here that is the cosine inverse of h bar omega, m, sorry, and the denominator is h bar square J plus 1x, that is magnitude, this cosine, okay, that is fine, sorry. Okay. Right, so that this is the hypotenuse, and this is project to this, so the angle between z and this vector is alpha m, so that's be this ratio. Then you can see here, this ratio is quantized depending on m, then the maximum value is when this m equal to j, but the h bar is cancelled, right? So that is, we can cancel h bar, so that is J plus 1, or larger or equal when m equal to negative J, right? So minus J over J plus 1. That is we can use for F to represent or to visualize the angular momentum in the space. That is given idea. Now, that is the general we discussed so far, and now we want to discuss some specific angular momentum. Here, that general means either spin angular momentum or optical angular momentum or some addition of angular momentum, like additional two angular momentum. That's chapter 7. But if this angular momentum always follow this, right? So that is general properties. Now, before we do the details, we have not discussed. Remember, we have introduced J plus minus applied this eigenstate for Gm. Will give us because it's either raising or lowering this state by 1 unit, so we have the coefficient. Right? We have not determined this one. So now, before we discuss spin, we are going to finish this. What happens if this J plus minus applied eigenstates of J square and Jz? We know it will change, it will increase by 1 unit or decrease when it's only on n. J doesn't change, right? So the coefficient we are going to determine. How to determine? We are going to use those relations. So that is first, right? So now first we know that J minus plus J plus minus, this is this one, right? And I'm going to use this. Is J square Z square minus plus H bar Jz. We are going to use this relation here. Second, if this, let's do this, if J plus minus, we are going to use inner product, right? So take this complex conjugate, that is, remember chapter 2? If we have this complex conjugate, this operator with the cat, so the cat is to be become bra, right? And the operator will take this complex conjugate, right? And the complex conjugate here just be, if you remember, this is not permission, it's complex conjugate, just change, right? Minus became plus, plus became minus. Remember we discount, and I think here, and let's get rid of this one. Just not permission. Okay, we are going to use this, and also we use this. So we're going to also use the also normal G M delta G prime delta M M prime. We're going to use this three. Okay, so now in order to do this, so we're going to use inner products of this. Then this bra multiply this itself, so that we have Jm. I'm going to immediately use this one, the Jm. J minus plus, that is bra conjugate this one and multiply itself. We look in this one, right? And this one, okay. Equal to this, right? So that is Jm. Right hand side Jm plus minus 1. Cjm plus minus complex conjugate and Cjm plus minus and Jm plus minus 1, right? Left hand side this. Right hand side is this one, right? If I just do the inner product. So now let's look at the left hand side. Left hand side, Jm, okay. Now we are going to use this, right? This is a product of J minus plus multiply J minus, J plus minus. Is here, right? So that is, okay. Then just immediately use this, right? Because you know what I mean is the left hand side is this term. J is square and minus plus H bar Jz. Okay. Now it's all the eigenstates of J square and Jz, so we can obtain this one by its eigenvalues. So here J square is H bar square J multiplied J plus 1. And this is H bar square M square. And just so that is H bar square J plus 1. First term minus J square, Jz square is H bar square M square, right? And minus plus H bar. J is another H bar N, right? With this. Then since those are constants, I take outside and then this Jm, according to the orthonormal, so that's equal to 1. So we have H bar square, all our H bar square take outside, that is J plus 1 minus M square minus plus N, right? That is left hand side. Okay, and then the right hand side, since here, this is the numbers, right? So I take outside, that is Cjm plus minus absolute square, right? The norm of this. And then Jm plus minus 1, Jm plus minus 1. And that also normalized, because we know this also normality of this eigenstates. So that is equal to Cjm plus minus square. So very easily, I mean, this is the idea, and if you deal with this kind of things, you just use the property here. So Cjm plus minus is equal to, okay, I take square root, right? So there's H bar and square root J plus 1 minus M square plus minus plus M. And that can write up either this way, okay. J plus minus 1 minus m, I take m outside, right? So this inside is m plus minus 1. Right? Here, m squared, I take more than minus m outside, so they have a minus m here. This minus became plus, and this plus became minus, right? Or another way, you take this, write down here. Oh, sorry, this is not square. H bar. Here, this is g squared g squared plus g, and this here m minus m squared minus plus m. So g squared minus m squared is g minus m multiplied g plus m, right? Then we have a g here, we have either minus plus m. So you can do another way is g minus plus m and g plus minus m plus 1. So plus minus correspond to this plus minus. So now let me summarize here. When the g plus minus apply the eigenstates of a g m, that give us, okay, let me just show, g plus, that is h, they follow this, right? The coefficient g minus m, right? And plus take minus, and g plus m plus 1, g m plus 1. Then g minus applied against that g m, you give us h bar, g plus m, here take plus, and then this take minus, and g m minus 1. M. So here g squared, m squared, then we have a g plus m, g minus m. So for this case, g plus m, and then this is a g, this is a minus m, so that is a minus. Take g minus here, so we have a plus here, that is plus 1. So let's see. That's g minus, yes. Okay. So now, when we have this, then we can calculate this, how about this one? How about this one? If we know g plus minus, apply to this, and this is not against the gx, right? But gx is half, use this relation here, right? This one, so we know that is a half of g plus and g minus, plus g minus. Then we know each individual here, so you can have this half, so h bar take outside, inside, okay, I just immediately write down this result since you know this one, right? So that is these two terms. So that is square root g minus m, g plus m plus 1, g m plus 1 plus g minus m, plus m, g minus m plus 1, g m minus 1. Similarly, y. So you can do gy. Gy is minus, right? So I just leave you to do yourself. Now, then let's consider what's the expectation value of gx, gy. If we know this expectation value of gx on the states, how much? Since this one, gx applied against the gm and give minus m increase, another one decrease, right? Then the bra is gm. So if they are not equal, it's equal to 0, right? So that is Okay. Okay, I have a space, let me just use space. Okay, so now. No, fine. The first term, this one multiply this one, right? H bar, half H bar, square root J minus M, J plus M plus 1, Jm plus 1, right? Second term, H bar, square root J plus M, J minus M plus 1, Jm minus 1. So since orthogonal with 0, that also makes sense if you look this graphic. You know the Jx is rotate along this because the eigenstate is not this one, right? So you will see that is the average of this. You give us 0 on states, any eigenstates of this. Okay. But how about the Jx squared? Jx squared is the product of these two, right? J plus J minus. J plus J minus. Just do this. Then we need here quarter. Inside J plus, so we have the J plus square. And then second one, J plus, J minus. J plus first, J minus second, right? Then the third term is J minus J plus. And plus J minus 2. Now, when you write the result and write the constant. So take the constant for quarter outside, Gm. Do you agree? Let's look at this J plus square. Because J plus, we know J plus will apply state Gm, will change M from M to M plus 1. Then we do again M plus 2, right? So if M plus 2, this carry M plus 2 but plus M. So they are also going to be 0, right? Similar for this one. So the only is 2 remaining. Now we are going to look at this 2. Use this relation here, right? So the product of J plus minus or J minus plus or J multiply J plus minus is this one. Then we have 2 terms, right? Here, the first one, I'm going to use this. This is a minus. The first one is J square minus J Z square. Because this is a minus first, right? Minus first plus. So minus first plus, so that is plus. And the second one is this minus, so that is plus J square minus J Z square minus H bar J Z, right? This cancel. This will have two. There are 2 factors, right? Then each one. So you have, let me just take this 2. So that is 1 half. And then so yes, this because it's eigenstate of the J square and Jz, right? So we can immediately got this. This is a half of. And then the eigenstate Jm is equal to 1, right? So that is H bar square J plus 1 minus H bar square M square, right? So if you take H bar square outside, then you have the result. Now 0 result. And that makes sense since Jx square that is absolute value, so that shouldn't equal to 0, but Gx is a vector. So you will see that is the average on the whole direction, the average has to be 0. Okay, similar for Gy. For Gy. Okay, yes, the index for Gn, Gy equal to 0. I want you to double check yourself. Similar result equal to the same thing. Check yourself. Since the expectation value of Gx and Gy actually they all are along this perpendicular to Gz, so this became the same. This as a symmetry, right? We get the same result. Okay, now after we discuss general, it is very easy to apply the special case. Special case we are going to discuss in chapter 5. One is spin angular momentum, another is orbital angular momentum. So now let's discuss spin first. And since they have the same property of general angular momentum, so all the things are same, but there are some special specifically for the particular case. So though these all are applied to this either spin or orbital angular momentum. Okay. First, we consider spin and how to introduce spin. Or the first one is proof the existence of spin. Because this is a pure quantum mechanics result. Cannot get this from this classical. Let's consider in atomic theory. We know if we have this axis here, right? If a charged particle or the electron, let's just since we consider other atom, right? Electron move about this nuclear. As a movement, right? So that it make this magnetic moment, and to distinguish the other magnetic moment, we use mu F. So if we know if we have the negative charge or electron move around the orbit in the center of nuclear, then we know it will generate the angular momentum. The electron also has angular momentum if we move around that circle. So there's angular momentum associated with angular momentum will generate the magnetic moment. So magnetic moment, from the atomic theory, we know the relation between this orbital angular momentum and this magnetic moment is like this. You can, let's use this operator. Since we consider, even in atomic theory, we use the idea of this general angular momentum. So we have this. Therefore, the Hamiltonian, when we play into the magnetic field, the Hamiltonian, the interaction between the magnetic moment with the magnetic field, there is generated additional energy, right? That is negative. This one, in the product of between the magnetic moment and the field. So what happened here? If you want to observe this, say if you have the item here, or B non item into the magnetic field E put here, so you will see this several deviation depending on the magnetic moment, how big it is. Depending on this, how big it is, which the direction, right? So that what you will see this split or deviate from this either upward or downward, depend on this this value, right? So how much here is depend on L, right? Because this split is depend on this, and then project, so that corresponds to, if I write down the more details, minus become plus E O M C L Z. This term, right? Assume that the field is along Z direction. So this product actually just LZ. Then you will see that the allowed value over which you measured is correspond to the HM, right? So you have allowed the split over the divided from the horizontal inside direction of the motion. How much is depend on M? M is minus L plus 1 until L minus 1 and L. How many? 2L plus 1. So we will have a split into 2L plus 1. But if you want to measure, depend on what kind of the orbit that L is. So you will have to look this. Now this is in general, but this in 2022, sorry. So we have famous physics, Stern and Dirac. Famous experiment. What they found is, okay, we have a beam. This beam is a silver beam item. Coming to the Mach field, and what they found, there are two slits, right? There are only two. And then, okay, try to use this to interpret it failed because L equal to 0 in this case. We know the silver atom, or as the closed shell, only the outside of the electron is on this s orbital. And s orbital, of course, I think you already know, right? Even though not we have not dealt with, but in the 500 level quantum mechanics, you know that L equal to 0 for s orbital, then so there's no split, right? Why we have two? And that means there are some the intrinsic. That means intrinsic. Properties, or just a scheme. Another motion, even though the orbital is 0, but still has the split. So that means there are another motion correspond to this dipole moment. I'm going to use mu s, which is associated with this angular momentum. There must be a spinning or a rotation. This one, when put into the Mach field, will interact with. So the Hamiltonian here is to distinguish this one, and with orbital angular momentum, we use mu s. So must have another term. And this term cannot be explained by the classical physics. This is really from quantum mechanics, because from quantum mechanics, later you will see that value corresponds to J equal to half. So because this phenomenon, and they say, okay, so that means this is an intrinsic property, right? And this is one of the features, because this, that means it's one, feature 2, this structure this. That means, for example, the orbital angular momentum we know we can write is the R cross product P, right? So we have a structure here. However, this just the electron itself is almost you can say, cannot determine the orbital with the size of the radius, right? It's electron itself here. So that is structure this. Then how to obtain this? How to describe this? Okay. So that is the second picture, and then we're going to analyze here. Okay. Introduce like this, because mu L is so we introduce the dipole moment due to this spin, follow the same behavior, but here, let me give you, if we introduce to distinguish the orbital angular momentum, we use S, but they are all the general angular momentum, right? All J, either J equal to L or J equal to X. But here, what we found, they do not equal to exact here. We need to add another constant here to make this measurement, or we define this dipole moment due to the spin, then the Hamiltonian calculate this, so we can measure it consistent with this one. And here, GS, we call this Landé factor, or the Jerry-Magnet ratio factor, or Jerry-Magnet ratio. That's we introduced. And later in chapter 7, we will prove this constant where come from. Okay, that's just keep in mind we have this one. Actually, for orbital angular momentum, we also have another factor. In that case, factor equal to 1. But here, just keep in mind here. Later in chapter 7, we are going to discuss. So, experimentally, is about 2. Then here, you can see here this the spin dipole moment is 2, right? So 2 is minus E or MC, since these two factors cancel. Okay, that is how I introduce the spin here. Now, since we introduce or prove the existence of spin, another angular momentum, then all the properties here should be followed. Now let's discuss in general. Then we are going to discuss the special spin case. So with this, now second, general spin theory, spin. Okay, now I follow the same thing here. Spin orbital angular momentum, spin angular momentum is vector. So it has x components, y components, and z components. Second, say we can also build up spin plus minus s plus minus equal to sx plus minus I s y. And the same thing here. Okay, so this also the commutator. Oh, sorry, conjugate, because it's not permit, right? So S plus minus star dagger is equal to S minus plus. Same thing here. So commutator S square. S J S K is I H bar S L. S L. And follow the same thing. J K to L. We follow the counterclockwise. Otherwise, you take if you opposite take the clockwise, you have to take the negative side. Then the others, S square, commute with any components. Then you have also the S plus S minus is 2H bar SZ. Then they are also S plus multiply S minus plus multiply S plus minus is also S square minus SZ square. And plus H bar is the all are same. S, sorry, SZ, S plus minus is minus plus minus h bar s. Okay. Then they join eigenstates, and eigenvalues. All follow the general property of the angular momentum. So we have s square. Now here, we are going to distinguish this. This G is the the quantum number for the J square, and M for the quantum number of Jz. Here we use S to replace G, and we use Ms to replace M. That is the notation for the spin angular momentum. So that is h bar square s plus 1 s ms sz is h bar ms s ms. Then here, these are all same, right? So okay. The S prime, MS prime, S, MS also orthonormal. Delta S prime S, delta M, S prime, MS. And they also complete. Consider S plus minus. S and S is big for h bar. S minus plus 1. I use another way, right? S plus minus n plus 1. S and S plus minus 1. So S n and S. Okay. Then similarly, if you remember, if you ask us to find the expectation value of Sx, because this is not eigenstate of Ss, so that gave us 0. Similar equal to the expectation value of Sy, but the expectation value of S square, xx square, is also equal to the expectation value of y square. Y square is remember that is half h bar s plus 1 minus ms square. Let's follow the similar for the z. Okay, so those all are same. Now we want to discuss some of the detailed case. So that means for any S can be 0, can be half, can be 1, 3 half, 2, 5 half. Oh. But here, it is fixed. Means not for given particle, so this is for all these fundamental particles. That we extend to from the electron, we extend to any fundamental particles like proton, like photon, like the ion. All the fundamental particle has its intrinsic spin, then they only have a fix. So for example, electron, this half cannot be take 0 or any other values. So this value is fixed. But in general, we didn't say this allowed. For example, later we look at outer angular momentum. This value is allowed all the integer values. Right? But here for the spin, it always fixed. For this fixed, then the ms is minus s plus 1, and increase until s minus 1 to s. How many? To s plus 1. Allowed value. That discovery is very important, so we can find in the quantum world, right? So we find, okay, the particles, not in addition to the other general particle which we can find or correspond from the classical physics, but this one pure mechanics. Okay, this is a general theory. Now let's discuss spin half case. If we discuss spin half case, you can extend or similar to extend to the spin 3/2 or spin 1, spin 2, any, right? So that's just since they are all general, but for given different spin, you have different value. Let's consider spin half. So for spin half case, we know S equal to half. How about MS? MS plus minus half, right? Because MS is minus here. MS from minus S, S minus half. Then minus half plus 1 is plus half. There's no anymore, right? That is this one. So there are only two values, and that also makes sense. MS, how many different? 2S plus 1 is S half, only 2. So there are only two, that is special case in this case. Okay, having states. So we have two states. One is spin half, S always, and MS half. Another spin half, but MS minus half. Only two states, right? Then this S square, apply the S and S. We will have H bar square S plus 1, S and S. And since S is half, right? H bar square half plus 1, S and S, which is, this is 3/2, this is 3/4. That is fixed. And then this SZ is plus minus H bar half. Right? Because MS is plus minus half. So those are all give us. If ask us the magnitude of spin in this case, we know that is H S plus 1, and that is H bar square root 3 over 4, right? Or this one. Okay, so that is we just from journal where we can obtain those. That for half. Now we are going to discuss how about the eigenstates. So here we are going to express this one, represent. How to represent? Representation.
Why are we keeping the SMS in the ket for those
Here. Here.
in the next step? Why is that still SMS when we put it
Which one didn't follow? You mean?
in? So aren't we plugging in for S and MS 1/2 and minus 1/2? If so, why do we still have SMS for our final answer?
When you go to your plus minus H bar over 2, cat SMS, far right of the board.
You're
Right
pointing
there,
at
yes.
Here, right?
Yes.
This because this okay. This MS plus minus, right? So here MS maybe plus maybe minus. But if you okay, if you run, let's just keep here. Okay, but just
No, actually, I meant the one above it. So you see how you
Oh.
plugged in 1/2 for S. Why does ket still have SMS? Why shouldn't it be 1/2 comma 1/2 or 1/2 comma plus minus 1/2?
this one,
No, the ket.
the cat. This is a cat here, right?
Yes. So you see how you went how in step 1 you replaced S with 1/2,
Yes.
but we still have S in the ket. Why don't we have 1/2 right there?
Yeah. Okay. Yeah, that's fine. I mean, that I just implied. Yes, you can just replace half of yes. That's fine. Or I mean, we already assume S is half, so that means this implies already half. Yeah. If you either use this one or use S. Okay, since we discussed this case, right? I just still keep general, but now you know that is half, yes. That is a fixed half. So here, if you want to write this way, it's also fine. Either half ms or s ms. Okay. So how to represent it? Can we represent in the position representation? No structurally, because it's structureless, right? Impossible to project on this or represent in the position representation or momentum representation. We have to present in the matrix representation. That is possible to represent this one, right? So in matrix representation, we need a basis. The basis of to build up this matrix, we use one is we have only two eigenstates, right? We use eigenstates of this S and MS. That is the eigenstate of S squared and MS. SZ. And since we know this eigenstates is orthogonal and complete, so they can build up this space, satisfied space as a basic vector, right? So we select the eigenstate of S squared and SZ with these two as this space. So the space is 2-dimensional, right? 2D dimension. Yes.
Is the absolute value there of S, is that the expectation value?
This one?
Right
This
there.
one, yeah, this absolute value, yeah.
Expectation
Oh, okay.
value?
Either use this equal, yeah, that is B equal to expectation value of, I use somewhere here, right?
Okay,
Yeah,
yeah.
same thing, yeah, that's it. Sometimes they use this means this absolute value, but of course it is, if more straightforward is like, that makes sense?
Yes.
Okay, so when that means the 2D, and now let's first write down in 2D space as a matrix representation. The basis is a cat, right? So the cat here, so just let's consider general. So in this space, right? So any vector that is this vector project to the space vector. That is 1, right? And this vector project to this one, the component 0, right? And the same thing, same, this is half equal to 0. Equal to 1. So that means any vector cat project to this space, this is the basic vector, and the components, right? So you can see so the basis vector here in this matrix representation is a column, right? And the column matrix is components 1, 0. That is the components of, I think, yeah, this one, right? This vector project to this is 1, project to this is 0, so that is a column matrix. And another one is 0, 1. That is the eigenstates of S squared and SZ in this matrix representation because it's only itself is the basis vector. Once we have this, now we are going to write down those, how to represent those operators in this matrix representation for the spin equal to half. Now we discuss on this case, right? So how to do that? Because remember, if this operator may go to the matrix representation, we need to calculate. We need to calculate the matrix element, right? Each of the matrix element is here, and okay, here, these are again the basis vector, right? So the key is you're going to find the matrix element. Once we know the matrix element, we can build up matrix. So let's look this S. Okay, let's look at the S star. S squared. X squared, the matrix element of. Now I'm going to use general. Then we just sub numbers very easily. S M S, S M S. Even though we know S is half, so because this eigenstate this one, right? So that is S M S, H bar square S S plus 1, S M S, right? Because this. That means this. Sorry, prime. In this case, S is same, so only MS. Since the S fixed half, right? So H squared S plus 1 delta M S prime MS. Right? If the two states are not the same, that must be 0 because orthogonal. If the two states same, then we give this. So we have the S square go to its S square. Now, when we do the matrix, we first remove this head, right? So that is this diagonal term, right? How many? We have only 2 by 2, right? So it's a 2 by 2 matrix. So the diagonal term, when the MS equal to, so this is MS half minus half, right? So that is a half. And let me see, usually we use top, it's a minus half. Then here, when MS prime equal to half, and MS half is this diagonal term, right? So that is this one. And S is half, so we have I take H bar square because it's a constant. Outside is 3 over 4, right? And then if MS prime is half, but the MS is magnified 0, 0. So very easily, we obtain, you can also take this outside. So we take outside because it's all the constant. Diagonal, and that makes sense because if the operator or matrix is diagonal in this corresponding basis, that basis must be the eigenstates of this operator or the matrix. The diagonal term are their eigenvalues, right? Like this. So that is how to write down this S squared. Now SZ, go to SZ. Again, we need to find, okay, first. Also, since SZ apply the eigenstates, it gives us H bar, MS, S, and S, right? So the SZ go to its matrix, also again is a 2 by 2 matrix. That's B. I take H bar outside because the same thing. And also diagonal, right? Same thing like this, diagonal. The first one, when MS equal to half, so that is 1. Sorry, I have half here. And 0, diagonal, and when MS equal to negative half, it's minus 1, right? So that is this. Intermediate step, I didn't write down intermediate step, but that is this one. This one is half minus half. Yes. Right. So there's 4. Okay, now next one, how about the SX? Oh, let's first S plus minus. S plus minus, we know that the formula we have already have this one, right? S plus 1. Okay, use this one for another expression. Minus ms plus minus 1 times ms plus minus 1. S ms prime is plus minus s ms is equal to S is half, ms plus 1. Here, S ms prime, S ms plus minus 1. Then you can see definitely is not diagonal. If ms prime equal to ms is equal to 0, only when ms prime equal to ms plus minus 1. So the S plus minus go to the matrix representation in this case is okay, to distinguish since we are not cannot give us same answer. Plus the plus is here we have X, right? And here this is a 3/4, right? So this is a 3/4. Here, if ms is half, here either ms is half, depending on this one, right? So plus minus. So there is another 3/4. So either it's the same sign or different sign. So we have very easily diagonal terms 0, since we cannot. And then for this s, this is plus 1, right? So that is m. This is so minus half plus 1 is this one, right? So that is this term non-zero is 1 here. And here, this is also 0. Okay, I think for this I got too fast. Let me give you intermediate like this. So you can reach this. You can have this. Now half s plus half and half is plus half minus half, then half minus half is plus half minus half is plus half minus half. Okay. So now let's look at this individual. This one will increase the ms from half plus 1, so there's no such states, right? So that is 0. Then this one, minus half plus 1 is plus half. So they are orthogonal, right? So that is this value. Then this value is when my ms equal to negative half, and negative half minus plus 1 is half, right? So then you can see this is 1/4, this is 3/4, so that is 1/2, square root 1/2. Right, so that is let me give the result. And then look this one. So this one again, when s plus this half plus 1, it does not exist, so this is 0. And this one again, this minus half plus 1 is plus half, but this is minus half, so that is 0. Only this one, and there is h bar here. Okay, so this one you can see here. This is 3/4, right? This is minus half, so it became plus. And this is another plus, because this is a minus plus half. 1 is half, so that is minus quarter. Plus quarter, right? Plus quarter plus 3/4 plus 1/4, that is 1. So that is 1 here. Okay, similarly, I just gave you s minus again, and let me just do the same thing. So half s minus half. This is the way which if asked you do, you know how to do that. again, we can do the same analysis here. Minus, so this one, when this go to minus half, right? You got this, it is here. MS minus 1, so this became a half minus half, so the orthogonal is 0, right? This term 0. They are not the same. Then this one is 0 because you cannot lower. This is already minus half. If minus half minus 1 is minus 3 equal to 0. Then this one exists because S minus is half minus 1 is minus half, so they are orthogonal. And the value, same thing, you can analyze what is H is 1. Then the last one, again, this is minus half, cannot go lower. What is this? Now once we have of S plus minus, so you can build up X, Sx and S1 very easily, right? Because we know the relation between X and Y. So now it's because Sx is half of S plus S minus. Sy is half I over S plus minus S minus. So Sx go to this matrix. You just add these two together. Right, so that is half of H. The first one is 0, 1, 0, 0 plus half of 0, 0, 1, 0. And then you have 2H, right? So that is H. Yeah, half H, right? Diagonal term is 0. Then Sy, you do the same thing. Is half, but this is I. Remember here, this denominator is I. Okay, and inside H bar, plus, right? Plus, still plus is here, 0, 1, 0, 0, minus H bar, minus 0, 0, 1, 0. Then you have H bar 2I, 0, 1, 1, 0. But now I multiply I inside. So I multiply I, then I never have a negative sign, right? So 0 minus I. Did I have a minus?
I think that's right.
Yeah, that's right. Yes, that's right. Okay. Now the remaining part. Remaining part, for example, ask you to calculate this expectation value. I think since I leave that application or example later, but now we are going to introduce Pauli matrix. Since for this spin half, there is a famous Pauli matrix, which is very popular and useful. So now let's introduce this. Let's summarize. S Z here, right? Half H bar 0, 1, 0, minus 1. S, okay, S X is half H bar 0, 1, 1, 0. And S Y is half H bar 0, minus I by 0. So you can see they have the same formula, same line. All has the same constant half H bar. The only difference is matrix. So I'm going to write down here. I'm going to introduce the matrix, Pauli matrix. I'm going to say, sorry, this is here. And this one is sigma x, and this one is what? Sigma y. So I introduce sigma as a Pauli matrix. This is only for the spin half. In the 3 dimension, it doesn't work. Right? I mean, this is just introduced for this 2 dimension and correspond to the spin half. So when we introduce this is a vector, so there's x component, okay. x component is this one, 0, 1. So you can see here, dimensionless, right? We just consider the factor of this dimension is half h bar. This follow the spin. Then the matrix just introduce the 2 by 2 matrix which is vector matrix, has 3 components. And these 3 components follow this commutator relation and some other properties which is useful. Okay, so when we introduce this, let's first discuss properties. First, and this one is very easy. Square of any components is equal to unit matrix, right? Example, let's say x sigma x squared, so that is 0, 1, 1, 0, 0, 1, 1, 0. And you can see this is this one is 1, right? 1, and this one is 0, this is 0, and this one is 1, right? Yes. And the others you can double check yourself. Second one. This one we call the anti-commutator, but let me just put sigma j and sigma k plus sigma k, sigma j. So you see the order different because this is a matrix follow the kind of operator behavior. You cannot, if they do not commute, you cannot equal to the order, right? So not equal to 0 if j not equal to k. Because j equal to k is this case, right? J equal to k is j squared. That is this one. So, but then this is very interesting. You see, this is a plus. This is not the commutator. If the commutator is minus, right? So usually this also can write this way. We call it anti-commutator relation. Okay. Number 3, if this commutator relation is like this, okay, the example that's just also being one example. That's sigma x, sigma y plus sigma y, sigma x. So that is, you see sigma x is 0, 1, 1, 0. Y is 0 minus I, I 0 plus 0 minus I 0. And 0, 1, 1, 0. This is 0, right? Sorry, this is I, right? I, and this is 0. This one is 0. This one is minus I, right? And the plus here, this one is minus I. And then 0, 0, I. So you see it cancel, right? Yes. Right? Okay, so now let's finish this one and we keep continuing on Wednesday. Commutator relation J K equal to 2I epsilon j k L sigma L. So here, this coefficient is, we call this equal to 1 if j k L is even. Even commutation. What does it mean? So if we have x, y, j, that is that's okay, right? Because x, y, j, you don't need commute, it's just from x, y, j. But if this x, j, y, so you have to, if we return to x, y, j follow, you need to permute once. That is R, right? But if you permute twice and then go back to x, y, z, order, then that is even. So in that case, 1. Then minus 1 is odd, like I said. So if you have a change is x, g, y, then you change the g and y, if you permit one case, so you have a minus 2i here. And this one is here. This is gy, so that is 1. That make sense? Okay, so this L is follow this order, but then this number either is 0, 1, and minus 1 depends. If any 2 are identical. Means if you have x, x, y, so there are 2 I, j, and k are equal, then that be 0, because they are commute, you have the same. Right, so I keep here, and maybe Wednesday we can play a little bit, so you have the idea about this. Okay, homework. Thank you. If not, I still can postpone to Wednesday. You can. If you finish, just you can change.
For some reason, I really thought you had said Wednesday in
Really?
class.
I
I
said,
thought you did too.
yeah, okay. Right, that's fine. I remember my gave the due date is 14, right? But fine. Wednesday you can turn on Wednesday, no problem. If you want, you still can keep. But if you think you are ready, you can turn to me. I'm going to grade it. And on Wednesday I plan to assign the last homework. So yeah, that's fine. Totally fine if you want to turn right now or you turn on Wednesday. But if I made it confused, sorry.
It's late in the semester. I don't know what I'm hearing half the time anymore anyway.
Yeah. Okay.
Surviving.
Yeah. Yeah. That is yeah. This is the mechanics. Okay. PZ. So your Hamiltonian. This is a total. Okay. Yeah. Leave it on here. Okay.
I can
Okay. All right.
Can you send
Yes.
me my email?
You send me email?
Yeah, I got the homework, but I don't know.
Maybe it's just before the class, right?
No, I sent it like last week.
Last week.
Maybe I sent it to the wrong email.
Oh, probably I didn't receive. Yeah, send me again.
I have a really dumb question. So right here,
Yeah.
obviously I get it, you factored out the age and all that, but, so, okay, so you subtract zeros or minus zeros. So why is this one end up negative? That's supposed to be,
Here.
that's what I was thinking, so you should have 1 minus 0,
Ah.
and here you have 0 minus 1, so your negative should be, right?
Wait a moment. There's a minus here.
Yeah.
Ah. Okay, minus
That'd
1.
be minus,
Minus 1 and rather than minus. So that's positive, right? Let's do this way. This is a minus 1.
okay.
Yeah, I multiply. Yes, okay.
I knew it was a dumb question. I just, for some reason, I couldn't
So
figure it
your
out without
question,
talking
your
it
email
out.
is about homework?
No, it turns out I sent it to the wrong person. It turns out there was someone at the
I
last
was looking, I was
institution,
like,
the last institution I worked with the same name as you, and I sent it to the
Really?
wrong person.
Okay, send me again.
bro.
Are you still writing?
Bro, keep it.
Oh, sorry,
I'm gonna
sorry.
Thank you. Because I'm the end.
Okay.
Last week we had